The next chapter is 5.3.4 Image Formation. In the previous chapter, we learned about lenses. The convex lens, the concave lens. The convex lens was also called the converging lens, whereas the concave lens was also called the diverging lens. We went through that in the previous lesson. Now we will go to image formation by these lenses. By the end of this section, you should be able to trace the paths of rays through lenses to form images. Understand the terms real image and virtual image. I think even in the IGCSE or O-level classes, you would have learned about the real image, about the virtual image. Use the lens formula to calculate image magnification. Image magnification. How do we do this? Now, in the O-level class or IGCSE classes, you would not have learned this. But we will learn this in the A-level IAL class. We will learn that today in this video. Trace the paths of rays through lenses to form images. Again, you would have also seen this in the O-level or IGCSE classes. What is an image? When rays of light coming from one side on an object are focused to meet at the same point, there will be an image of that side on the object at that point. In figure A, so let's look at this. Figure A, this is the object or the person, and this is the image of the person. You can form a real image of this person, or if we call the person an object, or then this image is a real image. It's not a virtual image, because if it's a real image, you can project it onto a screen or a surface. You can project it onto the surface, not into the surface, on the surface. For example, if you go to the movie theater, if you go to the cinema, you have a projector which is fixed behind the seats at the top. This projector will project the image onto the screen. That image is a real image. So the image that we project onto a screen, for example, using a projector, is a real image. Now, what is a virtual image? A virtual image is an image formed in the surface. For example, if you see your reflection in the mirror, or if you see your reflection in water, or even in a shiny surface, that image which you see in the surface of a liquid or a river, in a mirror, on a shiny surface, is a virtual image, because this image cannot be projected onto a screen. It is not a real image, it's a virtual image. Virtual images cannot be projected onto a screen. Real images can be projected onto a screen. So this is a real image. What is an image? So in figure A, the rays traveling from the boy's feet are refracted by the lens and meet again at a point on the screen. Previously we learned about refraction, and we saw convex lenses, concave lenses. We learned that the refraction occurs at the surfaces. So refraction occurs here and also here, surface, when it goes from one medium to another medium. The image of his feet will be at this point. See, the green lines are coming from his feet, so they will go like that. And remember how in the O-level or IGCSE classes you would have learnt how to draw the real image formed by a convex lens. So how do we draw it? We can use three lines. One line we draw parallel to the principal axis. Now in the previous lesson, if you're not familiar with these terms, principal axis, focal point, focus, principal focus, focal length, you should review the previous video, because we are going to use the terms that we learnt in the previous lesson for the explanations in this lesson. Let's see. So the point on the object or the person is here, then the corresponding point will be there, because all these green lines are intersecting at that point. So they intersect here, or they start here, and they intersect at the corresponding point from the object. So here this is the feet, here also this will be the feet that it will be pointing at. So how do we draw this? we draw a line parallel to the principal axis. What is the principal axis? Principal axis is the axis that is passing through the center of the lens and is perpendicular to that lens. So this black solid line is the principal axis. If we review previous lessons, even in the IGCSE or O-level classes, you would have seen the principal axis. Let me show you. This axis here is the principal axis. You see this dashed, this line here, and here F prime F, they are the principal foci. So principal focus is here. On this side also you have a principal focus. This principal focus is also called the focal point. Remember, we learnt it in the previous lesson. Focal point, focus, principal focus, all mean the same thing. When we draw a real image formed by a convex lens, we can draw three lines. One line, very easy, it has to be parallel to the principal axis. This dashed line here is the principal axis. So parallel to that, then it gets refracted. Once it gets refracted, we have to draw it passing through the center of the lens. Now if you look at this image, you might see that refraction here is occurring at the center, but it doesn't occur at the center, it occurs at the boundary or the interface where it goes from one medium to another. But why have we drawn it like this? Because that will make it easy for us to sketch the diagram. That's why we draw a vertical line passing through the center of the lens like this. Then we show the refraction at the line there. You see, this is a straight line all the way to this line. Then we draw it like this. But actually what happens is the refraction occurs at the surfaces. You see, it's actually this case, but to make it easier for us, we draw the line and show that it refracts at this vertical line. So one line parallel to the principal axis, then we draw it bending from the middle here, and this line should pass through the principal focus or the focal point F, also called the focus, focal point, principal focus, all mean the same thing. Then the next line we can draw it passing straight through the center of the lens without any refraction, just like that. Now where these two lines intersect is where the corresponding point of the object on the image is. This is the tip of the arrow. So here it will be the tip of the arrow of the image. That's what we mean by corresponding point. Now if you start drawing these lines from the edge here, maybe the tip here, then it will be the corresponding tip there. Okay, what about the third line? Now the third line is, we can say, is the opposite thing of the first line. Here we drew it parallel to the principal axis, then passing through the focus. Here we draw it passing through the principal focus, then parallel to the principal axis. So here and here we have horizontal lines. This and this pass through the focal point or focus or principal focus. The principal focus is the same distance on either side of the lens. The distance from here to here and the distance from here to here are the same. We call that distance the focal length. The distance from the center of the lens to the focus is the focal length. Now you know how to draw the diagram. Anyway, let's go back to this. So these are the three rays that they are talking about. The image of the feet will be at this point. Similarly, in an image of his head, an image of his head is also produced by the lens. This process will happen for rays coming from all parts of an object. So a complete image of the object appears. The rays shown in figure A follow these rules. A ray hitting the center of the lens continues in a straight line. See, continues in a straight line as long as it's passing through the center of the lens. You can see even this green line is passing through the center of the lens, so it is not deviated. It passes as a straight line, no refraction. Remember that. If it's passing through the center, there is no refraction. Then a ray parallel to the principal axis will pass through the focal point on the other side. See, parallel to the principal axis, passing through the focal point. Here is the focal point where it's intersecting the principal axis. Remember the focal point is at the principal axis, is on the principal axis. See, here it's on the principal axis, here it's on the principal axis. Then the third one, a ray passing through the focus on its way to the lens will emerge parallel to the principal axis. So it's the other way around. Here it's parallel to the principal axis, then passing through the focal point. Here it's passing through the focal point and parallel to the principal axis. The image we get is a real inverted image. Real, you know why it's called a real image instead of a virtual image? Because it can be projected onto a screen. Inverted means it's upside down. So it's a real inverted image. When light rays from an object meet again, an image will be formed. Only two rays are needed to find the position of an image. The third can be used for confirmation. So you see, even with two lines, even with just two of these lines, we can find the position of the corresponding point of the object on the image. But we can draw a third line for confirmation. As light rays forming the object in figure A actually meet at each point on the screen. As the light rays forming the object A actually meet at each point on the screen, the image appears on the screen. This is known as a real image and is common with convex lenses. So with convex lenses you can get real images, and also you can get virtual images with convex lenses. If you have used a magnifying glass, the magnifying glass is a convex lens. It's thick in the middle, thin at the edges. I explained the difference between convex lens and concave lens in the previous video. We are in chapter 5.3.4. I think in 5.3.3 I explained about lenses. So a convex lens is thick in the middle and thin at the edges. A concave lens is thin in the middle, thick at the edges. This is known as a real image and is common with convex lenses. Diverging lenses always spread the rays apart. See, the concave lens is a diverging lens. It spreads the rays apart. We saw that in the previous lesson as well, and here you can see this is a concave lens. It's spreading the light rays apart. It's diverging the light rays. So they will not meet at a point and so cannot illuminate a screen with a real image. By the way, I was talking about the virtual image formed by a convex lens, and I wanted to tell you about the magnifying glass. If you use a magnifying glass and look at the virtual image that is formed by the magnifying glass. Now how do you know it's a virtual image? If you use a magnifying glass to see something like read a newspaper, you will see that those images are enlarged. They appear enlarged. What you are actually seeing is not the newspaper text. You are seeing the image of the letters on the newspaper which are zoomed in. So that's a virtual image that of the text on the newspaper that you are seeing. So you are basically seeing a virtual image of the newspaper through the magnifying glass, and this virtual image is enlarged or zoomed in. So remember, when you read a newspaper using a magnifying glass, you are not seeing the letters of the newspaper, but you are seeing the virtual image of those letters in the newspaper. Or in other words, you can see you are seeing the virtual image of the newspaper through the magnifying glass. Diverging lenses always spread the rays apart, so they will not meet at a point and so cannot illuminate a screen with a real image. Figure B shows a virtual image being produced using variations on our standard image forming rays. So using variations. Now here remember we had 3 lines, but how do we do this? Here you can see this is the ray and it gets diverged. If you look at the previous lesson, you can see that. But in this case, to find the principal focus, we have the imaginary lines, or we extend the rays backwards until they meet at the principal focus. Okay, so here also you can see we can do that, and we can form a virtual image. By the way, let me show you from this book the virtual image that is formed by a concave lens. It's here. You see the same kind of picture is here as well. This is the object. You draw a ray parallel to the principal axis. This dashed line which is passing through the center of the lens is the principal axis. So you draw this, then it diverges. Now you extend this backwards. Then what was the second thing? You draw a line that is passing through the center of the lens from that point of the object, point on the object. Now where these two meet, the extended line and the line passing through the center, we will have the corresponding point of the object on the image there. So that is the tip of the arrow. So here it will be the tip of the arrow. Now this image is a smaller image than the object, because here we are using a concave lens. If you use a convex lens, it will be a larger virtual image, but here it's a virtual image because it cannot be projected onto a screen. So when you look through this, you will see a smaller image of this object. The image is virtual because it cannot be projected onto a screen. It's upright. Now if you see from this side, you can't even touch it. You can't get it onto your hand because you are seeing it from this side. What you are seeing is the virtual image. So there is no actual image on this side, but it appears as if it's there when you look from here. Virtual, upright, smaller than object. This is the virtual image formed by a concave lens. What about the virtual image formed by a convex lens? That is given here. So how do we do that? Now again, this is a little different, but we will see. Again, the two lines are there. Remember the line parallel to the principal axis and then passing through the focal point. Then another line that is passing through the center of the lens. So we extend these lines backwards and we get the virtual image. We get the virtual image of that object. So if you use a magnifying glass, which is a convex lens, you will see that the image appears bigger. So if you look at this arrow using this magnifying glass, what you will see is this, which is an enlarged virtual image, which we call magnified virtual image. And it's also upright. It's not upside down, it's the same way up, so we call it upright. Okay, let's look at this. Again, you can see the line that is parallel to the principal axis, and then it gets refracted. You can actually, when you're making the drawings, you can draw this straight line up to this line and then bend it that way. But you can see they have drawn it correctly. They draw the refraction here and again the refraction here. Within the glass, in reality, it's a straight line. So we extend this backwards. Then we draw the line passing through the center of the lens, which is undeviated or not refracted or bent. Then where these two intersect is where you have the corresponding point of the object on the image. So here is the focal point, also called principal focus or focus. Then this is the image. Formation of a virtual image by a concave lens. The orientation of the image is one of its properties. In figure A, the image is upside down compared to the original object. That's this one. We say it is inverted. It's upside down, inverted. However, in figure B, the image is upright. So you see here. Next one, image calculations. Next topic, image calculations. There is an equation that links the positions of image and object with the focal length of a thin lens. This is the lens formula. So remember what this applies to. For a thin lens, there is an equation that links the positions of image and object with the focal length of a thin lens. See, object distance, image distance, focal length. So see, object, image, focal length. U is that letter used for the object distance. We can say V is the letter used for image distance, and F is the focal length. You have already seen that in the previous lesson also, F. So let's see how we can use this equation. This equation uses a convention known as real is positive. As shown in figure C, all the measurements made would be positive. So all the measurements are positive. If a diverging lens is used, it would have a negative focal length value. Yeah, so you see here real is positive. So if it's a real image, then we have to take the positive values. If it's a virtual image, we will see. Okay, so as shown in figure C, all the measurements made would be positive. Here you can see it's a convex lens, so it forms a real image. If a diverging lens is used, it would have a negative focal length value. If a virtual image were formed on the same side of the lens as a real object, the value V would be negative. So image distance would be negative. We will go through this a little more so you can understand it better. So here are the labels for this equation. F is the focal length, that is the distance from the center of the lens to the focus or focal point. Then U is the distance from the center of the lens to the object. V is the distance from the center of the lens to the image. So image, object, focal length. This side also we have focal length because we have the focal point on either side of the lens at equal distances from the center of the lens. So the length of this F and this F are always equal for any lens. The focal length is the same distance on either sides. The SI unit used in the lens formula should be meters. However, as long as three variables have the same units, the equation will be consistent and correct. For example, if you measure U and V in centimeters, these values can be used in the equation to find the focal length, and the answer will also be in centimeters. What that means is, if you have everything here and here in centimeters, then this, if you calculate the answer using centimeters here and here, the answer to this also will be in centimeters, unless you convert it afterwards. Alright, now we will go to Unit 3 type of theory. Especially these investigations, experiments are tested in your Unit 3 paper. So let's go through this, investigating the lens formula. Now what is the lens formula? This one. So you should know this. 1 over object distance plus 1 over image distance is equal to 1 over the focal length. Very easy to remember. Using a setup like that shown in figure D, we can alter the position of the object and measure U. For each object distance, we move the screen back and forth until the clearest possible image is formed on the screen. So we move this until we get a very sharp, clear image, because if it's blurred or if it's not clear, that means that is not at the correct focal length. Because if it's at the exact focal length, the image will be sharp and clear. But if it's away from the focal length, the image becomes blurred and unclear. We then measure the image distance V. So you see, image distance, object distance, focal length is fixed. So we can move the screen, for example, and get the image distance V. So here you can see the lens is this, then this is the object, and this is the real image of the object on the screen. You can even do this with a magnifying glass. You take a magnifying glass, go outside, take a sheet of paper and try to project the image of the clouds onto the sheet of paper. Using that magnifying glass, you should be able to do it, especially when there is sunlight. Okay, without sunlight you wouldn't be able to do this. So on a sunny day, you go outside on a sunny cloudy day where the clouds are white and you have sunlight, then the sky is blue, then you can try this. You would see the images of the clouds and the sun forming on that sheet of paper. Using that magnifying glass, you can do this experiment. Let's analyze this further. For each u and v value, we need to calculate the reciprocal. This will then allow us to draw a graph of 1 over v. On the y-axis, see 1 over v on the y-axis, against 1 over u on the x-axis. So we move this here, 1 over u, which should produce a straight best fit line, where the y-intercept will be 1 over f. Lens formula experimental results graph. So this is the lens formula experimental results graph. Now let's see. By comparing the lens formula with that of a straight line graph, we can find the focal length of the lens by reading the y-intercept from the graph. So we can find the focal length of the lens by reading the y-intercept from the graph. Yes. So what we can do, we can vary these quantities. We can use different lenses, and we can find the we are not changing f. We can change v, image distance, and object distance, right? Yes. And then we can draw this graph. The y-intercept will be 1 over f. So this is what we have, 1 over v equals 1 over f minus 1 over u. Remember, this was the original equation. See, it's here also. Then since we want to make 1 over v y, we can do this. And now you see it's in the form y equals mx plus c. The gradient of this is -1. The gradient of this is negative. So that means it's going this way. If it's a positive gradient, the line will be this way. Since it's a negative gradient, the line will be this way. The y-intercept from the graph will be the value of the reciprocal of the focal length. So once you find the y-intercept, to find the focal length, you have to take the reciprocal of this. Okay, now we will go to the next topic, which is magnification. So far we have learnt about the virtual images, real images formed by lenses. Then we saw this equation, which is the lens formula. From this we can find the focal length. Now we will see magnification. When an object is formed, we can compare its size to that of the original object. For example, an image of a tree formed on the retina of the eye must be smaller than the real tree, or it would not fit into the retina. The magnification is a numerical value given to measure this size comparison. If an image is smaller than the original object, the image is said to be diminished. If the image is smaller, if the image is larger, we say it is magnified. So magnification is equal to image size divided by object size. Now if the image size is greater than the object size, we get a number which is greater than 1. If it's less, we get a number which is less than 1, between 0 and 1. So image size, I for image, O for object, divided by object size, M for magnification. Again, very simple. Note that units have not been included in this equation. Why? Because we can have the same unit here, they can cancel out. But again, this is image size divided by object size. Magnification is a ratio. How many times bigger the image is than the objects. That's why the units cancel out. Same unit in the numerator and the denominator, so they cancel out. Magnification is a ratio. How many times bigger the image is than the object. as long as the units on top and bottom of the fraction are the same, it will be correct. Here we have used the height as the size. We are using height as the size. Height as the size. So we are not using the actual size of the object, we are using the height. So height has a length unit. So for example, this can be centimeters, this can also be centimeters. That's why they are using h for size. Now normally the letter that starts with size is s, but here we are using h because it's not the size that we are actually considering. It's when we say size, it's basically the height that we are referring to. Any size measurement will be valid as long as it's the same dimension measurement on both image and object. So it doesn't need to be the height. So here we are using the height as the size measurement scope, but it can be a length, but it has to be the corresponding length on the object also. So it can be a depth, for example, but in the image also it should be that same dimension. Careful examination of the similar triangles in figure C. Similar triangles in figure C. Yes, so we have triangles. We'll show you that the magnification can be calculated from m equals v over u. Okay, so we have v, we have u, then we can see the triangle here. See, this is v. If you look at this, this is also the same length. If you look at this, you can see that is equal to u, and this is 90 degrees, this is also 90 degrees. Then so we can get the similar triangles, right? So this is the hypotenuse, this side, here 90, here 90. Okay, so learning tip: image properties can be real or virtual, magnified or diminished, upright or inverted. So you learned all these things today. You learned about the real image, you learned about the virtual image, you learned about magnified or diminished images. Magnified means the image is larger than the object. Diminished means it's smaller than the object. Now it can be magnified, it can be diminished, or it can be the same size. Then upright or inverted. Upright means it's the correct way up. Inverted means it's upside down. The image is upside down. Here upright means the image is the correct way. Is the same way as the object, not upside down. Okay, we have come towards the end of this lesson, and by the way, you can see here is a magnifying glass. So you are seeing the woman's eye using the magnifying glass, so the eye appears large. Therefore, if we do this in reality, we are actually seeing the virtual image of the woman's eye through the magnifying glass. Key definitions: real image can be projected onto a screen, is on the other side of the lens from the object. So two things here: real image is on the other side of the lens from the object, and the real image can also be projected onto a screen, whereas virtual image cannot be projected onto a screen, is on the same side of the lens as the object. Same side of the lens, okay, not a mirror, lens as the object. Magnification is a numerical value given to measure the size comparison between image and original object. Size comparison between image and original object. So magnification is image size or image height or certain image dimension divided by the corresponding object dimension. So if we take image height, here also we have to take object height, the same that is corresponding to the image, or any dimension. So for example, if you take triangle, for example, hypotenuse, and this also should then be the hypotenuse. If this is the length, then this also should be the length. If that's how we should do it. So it should be the corresponding dimension. Alright, we have come towards the end of that lesson, chapter 5.3.4. The next lesson is chapter 5.3.5, which is polarization. By the way, before we wrap up this chapter, I wanted to show you about forming these images. See, I have this which I can move. You see, now this is about, now what is this? This is a virtual image. So this is the image, this is the virtual image. Remember, the virtual image in a convex lens is formed if the distance is within one focal length, or if the object distance is within one focal length. If it is more than one focal length, then you have a real image forming. If the distance is more than one focal length and less than two focal lengths, so for example, here to here the focal length is about 80 centimeters. So from here to here, if you have another 80 centimeters, then you have the next 2 times the focal length here. So from here to here one focal length, from here to here another focal length. So if you like draw a dot there to show 2 focal length distance, then if you move this to that point, exactly 2 focal lengths away, then this will be the same size as the object. Object and image will be the same size then. If you move it more than 2 focal lengths, then the image will become smaller than the object. So if it is between 1 and 2 focal lengths, the image will be larger than the object. If it's okay, first we'll see if the object is within one focal length, then the image will be a virtual image and it will be magnified. If the object is more than one focal length but less than 2 focal lengths, then the image form will be a real image and it will be larger. It will be larger than so now you see I indicated 2 F points. See? Yes, we can also have labels. Yes, very good. Now see, the labels are there. Okay, all right, good. So now this we can form the 3 rays as well. See, this is a good side. See, many rays, no rays, principal, marginal. So 2 times the focal length, this height, and the objects will be the same size. If you move it more than 2 focal lengths away, then the image will be, real image will be less than the size of the object. So you can remember these things. Here I can even adjust the focal length. See, diameter of the lens I can adjust. So it's a good side that you can practice with. Can have a pencil, I can have an arrow. Okay, so you see, in the textbook we are using an arrow. Okay, and I can even measure with this ruler. See, so it's about 66 centimeters here. Let's see, you see it's about the same, 66. Okay, so that's the end of that lesson about image formation. And you can see more details even in this book. So how the real image is formed. Here you can see how the virtual image is formed by a convex lens. This was not in the other book, the A-level book, but it's in the O-level Cambridge O-level physics textbook. And you can also see how the virtual image is formed by a concave lens. Now we also have the eye. This here is the retina of the eye. So you can see the image is formed here on the retina, and it's a real image because it's projected onto a surface, onto the retina. And you can see the eye lens is a convex lens. It's thick in the middle, thin at the edges if it's a convex lens. Okay, so that's the end of that lesson. Again, what did we learn here? We learned how images are formed, virtual as well as real using convex and concave lenses. Then we saw the lens formula, 1 over object distance plus 1 over image distance is equal to 1 over the focal length for that lens. Then we saw how we can sketch a graph like this and put it in the form y equals mx plus c. The y-intercept of this will be 1 over f. Then finally we saw magnification. Magnification is equal to image size divided by object size. Now if the image size is greater than the object size, then the numerator is greater than the denominator and we get a number greater than 1. If it's less, we get a number between 0 and 1. So if it's a magnified image, the result here will be more than 1. If it's a diminished image, it will be a number less than 1, greater than 0. And you can use any dimension on the object as long as you use the same corresponding dimension on the image when you do this, when you use this equation. Alright, so we have come to the end of that. Make sure you answer all these questions and check the answers at the back of the book, or check the answers as well so that you know you did them correctly.